Okay, all right. So, hello and welcome everyone to whoever is listening to this particular podcast on YouTube, Apple, Google, Spotify, or any other platforms. I am Shah, and I invite machine learning engineers, researchers, and entrepreneurs to talk more about their current work, insights about their journey, and getting started with it. For this particular podcast, I have with us Dr. Natasha Jacques, who is currently a research scientist at Google Brain and a postdoctoral fellow at UC Berkeley, where her research interests are in designing multi-agent reinforcement learning algorithms while focusing on social reinforcement learning that can improve generalization, coordination between agents, and collaboration between human and AI agents. She received her PhD from MIT, where she focused on affective computing and other techniques for deep reinforcement learning. She has also received multiple awards for her research works that have been published and submitted to venues like ICML and NeurIPS. She has interned at DeepMind, Google Brain, and is an open AI scholars mentor. So, thank you, Natasha, for being here, and welcome to this podcast.
Well, thank you for having me. Excited to be here.
All right. So, just to learn more about your current works and your projects, can you tell us a bit about like what kind of projects you are working at Google AI as a research scientist, and what does the work routine look like for a research scientist at Google?
Sure, yeah. So I can tell you a little bit about a paper that we published at NeurIPS recently, and it was actually just posted in the Google AI blog today. So that was fun. But the idea is basically to use a multi-agent approach to improve single agent learning and generalization. And when I say agent, I mean reinforcement learning agent. Um, and so the idea is that RL is sort of only as good as the environment that you train it in, right? And you can, if you want to do a real world task, you can either try to collect expensive data from the real world, which is inherently going to be limited, or you could try to train in simulation and then transfer to something in the real world. But it's pretty hard to build a simulation, a simulated environment that's going to cover all of the complexity of the real world. And so what people have done in the past is they've tried to take some approaches for automatically expanding the simulator. For example, domain randomization just randomizes parameters of the simulator. And then you hope that that randomized distribution is going to cover everything that you might be tested on in the real world or at test time. But we show in our paper that this actually has some problems. So domain randomization isn't going to focus training time on the hardest test cases. It's just going to spread training over that entire random distribution. So there might be something within that distribution that isn't sampled very frequently and your agent is very bad at. So maybe you could do something smarter. Maybe you could learn how to set the parameters of the environment with another RL agent. So kind of take an adversarial approach. But the problem is that a purely adversarial objective for designing environments is kind of the wrong objective, because in many environments, it might be possible to just design an impossible environment. So you're minimizing the performance of the agent, you're succeeding at your objective, but it can't learn, it can't solve anything.
Right.
So then our approach is this new idea for training environment generation with minimax regret. So basically what we do is we have an adversary agent that learns to set the parameters of the environment, and it tries to maximize the difference between a pair of agents. We call our approach paired. So I can go into more detail about how it works if you're interested. But
Yeah, definitely. Feel free to include more information. I'll definitely love to learn more about that. Yeah.
cool. Yeah. So basically, the idea is that the adversary is trying to maximize the regret, which is basically the difference between these two agents. And we basically take our main agent we're trying to train to be robust, and we call it a protagonist. And then we call the other agent an antagonist because it's allied with the adversary. And so what the adversary is trying to do is maximize the performance of the antagonist while minimizing the performance of the protagonist. And the antagonist acts as like a flexible measure of what kind of performance could be possible in each environment. So it ensures that the adversary can't create impossible environments. It has to create environments that at least the antagonist can get a high score in. But it still gets to minimize the performance of the protagonist, so therefore exploit weaknesses in its policy and train it to be more robust. So the nice thing about the regret objective as well is it lends itself to generating a curriculum of increasingly difficult tasks, because basically, let's say the protagonist can't solve anything, it's just getting 0, then the regret just depends on how well the antagonist can do. And the antagonist is going to get a higher score in easy environments. So basically, the adversary is always searching for the easiest possible environment that the protagonist can't solve yet. So that lends itself to creating this nice curriculum of tasks. We show that the curriculum emerges, it's nice. And then when we take agents trained with paired and test them on a series of challenging test environments, we see big differences in how well paired performs versus like the mini-max adversary or domain randomization.
Yeah, that's a really nice influence. I guess it comes from the influence of, and I definitely like the words protagonist and antagonist much more than the generator and discriminator. So definitely, I mean, I have a very limited knowledge in reinforcement learning in general because I work mostly on the medical imaging aspects. But yeah, this is really interesting because I'm trying to learn more on GANs, and like it has a GANs are much more influential in this particular aspect of protagonist and antagonist that I can imagine.
Yeah, exactly. So the analogy to GANs would be that the adversary here is the generator. So it's trying to generate an environment. And then instead of a single discriminator, we have these two agents play the environment. And that's where we get the generator's objective.
Right, right. Right. And to slightly deviate on our other question that I had was, you have worked at different places, which involves different kinds of research environments, like taking DeepMind versus a PhD student as an MIT, and then currently postdoctoral at UC Berkeley versus definitely a research scientist at Google AI. So in terms of what are the key differences that you have seen in different research environments, how have you seen yourself adapting to different research environments that typically people might not know, like not a lot of people would have a diverse background of working at different places like you. So have you noticed something different in all of them?
Yeah, I mean, every lab is different and has a different culture. I think the only universal is that every time that I start in a new lab, it takes a little while to adjust, and I'm always like a little stressed out and trying to like learn the ropes. I don't know if that happens to you as well, but yeah.
Yeah, I mean, I'm fairly like my work is like maybe I just have one or two experiences, so definitely much lesser than that, but yeah, definitely that really makes sense.
Yeah. But I guess I can answer like more specific questions if you want. I mean, I think they're all great labs to work in, but they have different pros and cons. So.
Oh, so like as in pro and cons in terms of what the research projects that you work with, or is it the way the research is being approached over there? What do pros and cons means over here?
Well, I guess if I can, well, I don't know if we should actually go down this road. I was gonna say like, yeah, the difference between like Brain and DeepMind, for example. Like Brain is much more bottom up, so everyone can kind of pick their own research direction, and it's about like trying to get people interested in what you're working on, and driving research from individuals into forming teams and upwards. Whereas like DeepMind is much more top down. It's like the organization has OKRs and goals that they want to achieve, and like they think this will be important to get to AGI, and therefore a whole team is working on this, and so you actually just have to fit your research into like the team's broader goals.
That makes
I don't know if that's what you were asking, but
yeah. It's like the only the rationale behind that question was I've seen like definitely research varies. Like as a PhD student, if you are working with universities, you have a different dynamic. Like the end goal of a research is something on the science of like discovery, but versus how the industries work is towards much more reliability. Like you have to make sure these systems scale well and on those lines. So that is one thing that I have noticed. So yeah, definitely. And I haven't had a fortune to work to speak to a person who has worked within the DeepMind. So yeah, definitely, it's only the media articles that we read from DeepMind. So, yeah.
Well, I mean, I love both actually. And they both are great places to work, and there's a ton of smart people to collaborate with at both, and it's great. I don't think I would hate for you to think that like either Brain or DeepMind is too restrictive on what you have to work on. Like you certainly don't have to work on scalability or reliability, and at least like I mean, there's a lot of research freedom in Brain to pursue whatever you want, and like DeepMind is interested in very like big abstract questions. Like your research can be pretty far out, I think. So
yeah. And going back to one of your papers that I really liked, then maybe that was the paper that I was reading and that really intrigued me to have you on the podcast, was your paper on the social influence as intrinsic rewards.
Sure. Yeah.
So can you tell me a bit about, like, can you tell us a little bit more about, like, what is the basic idea of that paper, and how have you modeled intrinsic rewards to influence to have influence in between multiple agents?
Yeah. Okay. So first I can tell you why. Well, I'll tell you how we modeled the social influence, and I'll tell you how it connects back to intrinsic rewards. So the idea was that agents in a multi-agent system would get a reward if they take an action that causally influences the behavior of another agent. So how do you compute the causal influence of your action on another agent? Well, what we did is we just trained a predictive model that says, given everyone's action at time step t, as well as the state, predict what everyone's going to do at time step t plus 1. And then you can use your model. You can say, okay, what if I'd actually taken a different action at time step t? I can simulate this counterfactual action. I could say, if I'd done this, under my model, I predict the other agent would have done this instead. And so then if you take all the possible counterfactual actions you could have taken and sum over your prediction of what the other agent would do, you get this like marginalized prediction of the other agent, sort of what it would do if it were ignoring you. And then the KL divergence between the marginal policy of agent B, what it would do if it were ignoring you, and the thing that you predict it would do given your actual action, is a measure of the causal influence of your action on agent B. So you kind of see how much your action caused B to diverge from its marginal policy, its default policy, if you will.
Okay.
So that's like the influence. Yeah.
Okay. I'm trying to, because again, I'm trying to see it from a new lenses. How I like, because I work with a lot of basics of game theory. I'm trying to see if at all, let's say there are 3 agents, and if I consider what the other players might do, and if accordingly if I change my policies, do we have a kind of a situation which is the best case scenario that might happen, and accordingly the agent behaves? Is that the case, or is there not one scenario that the agent comes up with? Is it an ever-changing thing? I don't know if the question makes sense or not.
I think it would be changing because it depends on the other agent's policy, right? So as the other agent is learning, what you could do to influence it may change. Maybe if the other agent's policy is stable, then it does become fixed. The interesting thing about game theory, I think if you look at influence in something like Prisoner's Dilemma, or a Matrix game, it doesn't have a clear benefit. I think it wouldn't actually work in Prisoner's Dilemma. But yeah, so we show that it works in these spatially and temporally extended social dilemmas, which are more like, they're like a tragedy of the commons, but like spread out over space and time. So there's a common pool resource, right? Which are in the games we're testing, there's like apples that you can eat. But if you eat the apples too quickly, if all the agents eat the apples too quickly, they become depleted and don't grow back, right? So each agent is greedily motivated to eat as many apples as it can. And it will actually get a higher payoff if the other agents are abstaining and it greedily eats more apples. So, you can look at the shelling diagrams and show what the payoff is for following this defecting strategy. But if all the agents defect, they deplete the apples and actually they get much lower reward. So it truly is like a social dilemma type of environment. And we found a really interesting result from training agents to influence each other in this environment, which is basically that they learned to use their actions so the environment is partially observable. You can't always see when there are apples available if they're outside of your field of view. What our influencer agent learned to do is actually use its actions to communicate about whether food was present. And this allowed it to gain influence over the other agents, because if it communicated that there was food, they might change their action to go get the food.
Right.
So we basically found that the influence reward was incentivizing communication. And we then did a follow-up experiment where we trained agents to communicate, to learn communication protocols with the influence reward. And we found that they learned better communication protocols and once again achieved like higher cooperation in that environment.
Right. Right. Yeah. Yeah. Definitely. I'm just curious on my end. Like, I'm trying to see if this situation can be modeled using game theory approaches. But yeah, I maybe I need to learn more about that, because even if you see the prisoner's dilemma, we have an equilibrium point which can be only achieved if we have prior information of the other agent. So player one should have some information about the player two. Only then the equilibrium should be or could be reached, and all those things. But yeah, that's just a curious mind thinking. But yeah, I need
Yeah.
to learn more.
Well, if you end up analyzing that, I'd be curious to hear the results. I just spent a little time looking at like if you directly added the influence to the payoffs of Prisoner's Dilemma, and it was about whether the person changed whether they were going to cooperate or defect based on your action, then you could get a, like, let's say they were playing tit for tat, you would actually influence them more by defecting and then cooperating and defecting and then cooperating, which would be suboptimal. If you think about it.
Yeah, yeah, definitely. I'll look more into it. But one question that I had, because the thing that really intrigued me for this paper was, can you tell more about like what was the intuition behind using that? Like, how did the idea spurs into your mind to use these influence between robots? Was it something that you figured out technically and then labeled it using the terms of cognitive psychology, or like what was the inception point? Like, did you refer to cognitive psychology first and then maybe said like, okay, can I map to technical terms, or was it something that you figured out as a roadblock in technical jargons and then said, hey, this is what even cognitive psychologists might have to say? What was the path that you took for intuition?
Yeah, that's a great question. So I think the best way to explain why this works in terms of intuition, which is not the question you're asking, but I'll answer that in a second. The best way to explain why this works is we can show in the paper that this relates to rewarding agents for having a high mutual information between their actions. And that kind of makes sense because a big problem in multi-agent is there's a combinatorially explosive cost of exploration. So if you think about the joint, like if you have a certain number of agents, the action space expands exponentially with the number of agents. Finding the right policy in the joint action space is very hard. Like all of the agents have to simultaneously try the right action for you to realize that it's a good one, which is much less likely to happen randomly. So you can think of this as like an exploration incentive that makes agents more willing to try coordinated policies, which I think makes more sense. The other piece of intuition is like, if you're familiar with the intrinsic motivation literature. So the idea behind intrinsic motivation is in RL. I think RL is a great framework. It's very general. The problem is you need a reward function to optimize. And in many problems, it's like, what is that? Like, what is a baby's reward function? What's it optimizing? How is it learning? And so intrinsic motivation tries to answer that by saying, like, maybe the baby is curious, and that's what it's optimizing for. Or maybe the baby is seeking empowerment, which is like a very specific intrinsic motivation that's saying maximize the mutual information between your actions and your future state. So basically, what that does is say, you want to keep your options open because you're maximizing the entropy of the state. So you want to be able to enter lots of states, but you want to be able to do that in a very controlled way. So the next state you enter should depend heavily on your action. So you're minimizing the entropy of the next state given your action. I'm saying math out loud. I always hate when people do that to me. Sorry. But
that makes sense, yeah.
Okay. But so yeah, we should get a whiteboard. That's what we need. But yeah, so that's an intrinsic motivation that's been around in the literature for a while. It's hard to compute. Computing the mutual information between your action and a high-dimensional next state is tricky. But the social influence is the mutual information between an agent's action and another agent's action. And if you're in a discrete action space, that's actually pretty easy to compute. So I think that provides like more intuition about why this should work. If you're asking me how I came up with the idea, I'd have to send you I was doing my qualifying exam. We had to do like a 24-hour take-home exam. So Nando posed me this question, which was like, what other intrinsic motivations could there be? And are there any social intrinsic motivations? And I was like, and it was 4 a.m. and I'd stayed up for almost 24 hours and drinking a lot of coffee. I don't know. It's in a document somewhere, but yeah.
Oh, Yeah, yeah, that's an important piece of information. I didn't knew that, because I guess the time crunch that you had really made you think out of the box, and maybe that led to this structured way of saying social influence, I guess.
Yeah, yeah. I think it's also like I was thinking of like, okay, well, I could go on a very crackpot-y rant, but it's a little bit out there if you're
I would love
interested.
that. Yeah.
Okay. So the thing I keep thinking about is like I or I think this informs a lot of my research agenda, like somewhat indirectly, but I've been reading a lot of books about like human sociology and history and psychology, and it seems like what really distinguishes humans from other animals is that we're such a powerful social learner, and we gain so much from like integrating in societies and sharing information within that society. And so I'm really interested in this question of like, given our social environment, like what motivates us to like innovate new ideas, right? And I
Hmm.
think you could make a case for like social influence in that sense. It's like you want to come up with an idea that people build on. You want to write a paper that people cite. So it's sort of like you contributed something that influenced the future research direction. Um,
Well,
but that's a bit out there.
yeah, yeah, definitely, that makes sense. Like it's more like whatever work I do has to have some kind of reward structure that deals with other people in general, like how we do. Like if I do something, I have to have some kind of gratification based on other people's actions to that my action. So yeah, yeah.
Yeah, I think that's very true. Like, I mean, obvious intrinsic motivations you could build for these types of social dilemmas would just be like empathy, which actually the group at DeepMind is exploring. So they have this like uh, what is it? Inequity aversion resolves intertemporal social dilemmas, and it's just that agents don't want to have a reward that's too much higher than the group average or too much lower than the group average, which I think is a perfectly sensible intrinsic motivation. Like, I think that's true. People do feel guilty or envious, and that does motivate them. But the problem with that, from a practical perspective, is that you need to know everyone else's reward to be able to compute that. And if you
Hmm.
already know the group reward, why not just optimize it?
Right.
Right? So the nice thing about social influence is you don't have to see other agents' rewards. You just have to see the actions they're taking in the environment, which I think is a much more realistic assumption, especially when you think of multi-agent problems like autonomous driving, right? Like I always say this, like the Tesla car won't be able to observe the proprietary reward function of the Waymo car, but it
Hmm.
can observe whether it turns left.
And one because this brings me to a question that was is like, is it possible for, at least for the current state of art of reinforcement learning models, is can the model or agent have more than one rewards underlying while it is trying to take its action? I don't know, this is just an open-ended question. I again take that question from a very naive person who understands reinforcement learning, because when you said those questions, it made sense, like how we take actions has to have many multiple rewards. Like it's not just one thing that I'm doing because I just have one reward function. So do these agents, can we have agents modeled using multiple rewards?
Yes, definitely. So,
Okay.
in the social influence paper, we just take the environment reward and add the influence reward. You
Okay.
can sort of add up any series of rewards that you can compute and just optimize for that.
Hmm. Yeah, yeah, that makes sense. And I really appreciate the crackpot-y approach, because that was the actual
Mhm.
intuition behind my question. I really, because if you look at a glance of most of the deep learning algorithms, first of all, neural networks, GANs, apart from that, all of those research papers are mostly applied research. But if you see these big architectures that came up, it has a very intuitive uh, way of solving those ideas, and that is like definitely a crackpotty idea for those researchers too. So yeah, that is one thing I really appreciate. So yeah, thanks for sharing that. And,
Yeah.
and and one last flake to that question would be, what was the application you had in mind? Like were you having an application, like if I did this correctly, this thing is definitely gonna change, or I hope is definitely gonna change. So what are the big applications that you had in mind, and what are the possible things that you see now that it can be applied to?
Yeah. Well, so I'm a bit guilty in that I don't think I had a specific application when I was like, when Nando posed that question, like, what's a good intrinsic motivation? In a sense, like the intrinsic motivation question is like, in the absence of an application, how do I learn?
Yeah.
Right? Like I just am in the world. I don't know what I'm supposed to be doing yet, but what kind of priors could I build from interacting with the world? So that was sort of where that was coming. And just to say again about the motivation for the idea, I thought of a better way of explaining it, which is basically like I'm obsessed with the idea of like counterfactual impact. So like counterfactual research impact, which basically I mean like, if you didn't write this paper, how quickly would someone else write it? So if the answer is very quickly, then the counterfactual impact is low because it's replaceable, right? Like someone else would figure out how to do it. So I think to me, the research is really interesting is like high counterfactual impact. It's something that nobody else would have thought to contribute, I guess, or it's like very unique. So I think that's also like where I was coming from. But anyway, sorry.
Yeah. That makes sense. Yeah, definitely. And well, and one of the key things that when I was looking at the papers along the lines of multi-agent reinforcement learning was a question that really comes up. And again, don't pick me if I'm really bad research on this particular topic. And this question is generalization in reinforcement learning. It becomes a big problem for most of the researchers. A lot of people pose, and from what I understand is how well does a particular framework generalize in different environments. So do you think as of now the current state of art is are we getting close to having generalization answers, or that a researcher can say that, hey, yes, I can have a model that can generalize well across a variety of environments, or are we still far off from that moment to say?
Well, personally, and others would not necessarily agree with this, I think generalization in RL is a huge problem. And so I'm very interested in how to improve it. So that's the focus of our recent work on paired. That's actually, I would argue, intrinsic motivation relates back to this too, because it's saying like, rather than fit each new application, like, try to come up with something that gives you a good, strong prior that could then maybe be deployed to multiple different applications. But yeah, I mean, I think deep learning is very promising in terms of being able to really accurately fit large scale data and interpolate within that data in an impressive way. And we just keep seeing the evidence of this. But if you don't have a massive amount of data, it becomes a lot harder. So if you're trying to do RL for real world problems, unless you're at Google scale, it becomes a lot harder. Or you depend on a simulator, which again, now is imperfect. So I do think there is an issue there. And so a lot of my recent work has been focusing on trying to improve generalizations, actually. And I actually think, go ahead. Sorry.
Go ahead, please. Yeah.
I actually think social learning is a way that humans improve their generalization. So, if you take psychology classes, you learn about like humans having schemas or something. So if you go to a new, coffee shop and they have a different form of cue, you don't instantly know what to do, but you can observe what other people are doing and follow that. And it helps you adapt. Or, they talk about like Anka Dragon has a really interesting paper about self-driving cars. Imagine you're on the road and some crazy situation comes up that the car has never trained on, but it observes that all of the human drivers are like pulling to the side of the road or slowing down. What's a sensible thing for it to do? It's to copy the human drivers.
Right.
So I think this like taking cues from other agents that are in your environment and know what's going on is a great way to like adapt to changes in your environment. And I think that whole direction is relatively underexplored.
Actually, like a follow-up question to that is because I'm a huge believer of like taking inspiration from already biological, I would say, bodies on Earth. And but this is one thing that I, even when I started my PhD, I took psychology 101 because I was just intrigued by similar kind of inspirations that I would might want to take into research. But one thing I learned is we shouldn't take inspiration from biological bodies because they might not be the best optimized. And apparently the idea of deep learning is to have the best version that is technically feasible and not to take. So I'm curious, like, what do you like? Do you have those debates in your head, or do you believe that, yeah, like you said, like social learning is kind of a roadblock that could be case while designing new architectures? Like, I would love to learn more about that, like your personal opinion on that.
Yeah, I mean, that's a great point. And of course, you probably heard this so many times. Like, if you're trying to build a machine that can fly, you don't need to start with building feathers or whatever. Like you don't have to exactly
Yeah.
copy the existing biological mechanism. But with social learning, I basically see like there are other agents in the environment for a lot of problems we want AI models to do, like driving, and they have information about the task and how to do the environment. They're a source of information. So it's sort of up
Right.
to you, like how you want to architecturally encode that information. Like it doesn't have to be using a brain that's identical to a human, but in some sense there is like information there.
Hmm.
And I think that sort of extends beyond architectures. Yeah.
Hmm. Interesting. Yeah, yeah, definitely. And one other question that I had, and again, for people who might not know, for example, we know a lot of computer vision algorithms are being deployed in a lot of industry applications right now, like healthcare and many other sensitive areas that maybe 4 or 5 years back it wasn't even thought of that we could
Mm-hmm.
use neural nets in these applications. What are some of the what are some of the applications that you think deep reinforcement learning is being currently deployed versus that you think in the next, let's say, 5 years you might see a huge increase in usage? So can you shed some light on more on that? Like even like personally, it's a bad part on my end. Like I personally don't know many of the algorithms apart from like AlphaGo or something like that. That is definitely not a end user application. But what are some of the applications that you can say or speak
Yeah,
on?
that's a great question. So I mean, RL is being used extensively in industry, but mainly to like serve ads. And that's also if you think like a bandit counts as RL. Like I think ads are mostly served using bandits, which are sort of like a simpler model. But and I think like large scale deployments of DeepRL for like really practical problems it is a bit lacking. Like I don't think it's realized its full potential yet. I don't think RL has had its like ImageNet moment, let's say. But I'm really excited that it could. Here's some things that it could do. So there's people working on RL for making healthcare decisions. So Joel Pinot has a really interesting thing about like if you want to prevent seizures, you can stimulate the brain, but you don't want to stimulate the brain too much. And so it's a sequential decision-making problem where you want to plan your actions over time. Perfect for RL. She has results on that. Susan Murphy at Harvard is doing similar stuff. I'm really excited about RL for sustainability and climate change.
Mhm.
So you might have seen the big result that DeepMind and Google had as a collaboration of like minimizing data center energy usage using RL. The sad thing is, I think that turned out to work better with a simpler model, but I still think there's a lot of potential there. One thing is like managing electrical grids. So the way electrical grids work is a lot of the renewable low carbon sources of energy that you can have, like solar and wind, are variable. Like they depend on external factors, right? So you need to keep some amount of high carbon something in reserve, at least for now, because we don't have like good batteries and stuff. So you've got some like high carbon coal or gas plant in reserve, and you want to minimize that, but you don't want any brownouts or blackouts if the solar goes out. So this kind of like sequential managing of the grid, and there's actually more grid related decisions you can make, like turning off different buses or switching them. So like grid planning, grid optimization, cool RL problem. Um, what else? I thought of a few others. Anyway, I'm excited about it. I think there's a lot of. Oh, doing a. We did a follow up of our paired work on training an agent to learn to navigate the web for you. So it
Hmm.
clicks through web forms and fills in you say, okay, Google, go buy me a keyboard, or okay, Google, go book me a flight to Los Angeles. And it goes in and like clicks through the different web pages and puts in your info and then could like purchase you the thing. Um,
Oh,
so this type of thing. So we're actually actively working on that. We have a paper on that as a follow up to Paired, which is out. So you can check that out.
wow, wow. The last one is really interesting. That was like, yeah, definitely a unique, like a novel idea. I couldn't think, but yeah, definitely it makes sense. RL could definitely be a part of that. Yeah, yeah. Thanks for sharing. And go ahead. You were trying to say something?
Yeah, I was just gonna like clarify, like I do think RL is a super general framework because it's sort of like you're making a series of decisions to optimize for the long-term utility across the whole lifetime of your decision making. Um, and so it's like it's very broad, right? You know,
Yeah.
inevitably, if you have any sort of like sequential decision-making problem, I think a lot of these tools are going to be useful.
Yeah, definitely. And one other question that really brings to me, like when you mentioned you're surprised that not a lot of applications are using RL right now as of like 2021. Do you think when we are using deep learning for reinforcement learning, and deep learning poses one of the biggest problem, that is interpretability, like trying to explain what these models are really doing. For example, I can think of when deep learning is being learned, and if let's say a model is trying to act in a certain way based on other people's actions, like you said, the social influence, it's trying to learn what the other agents are doing. Does the deep reinforcement learning architecture has its own way of saying it back to the users what it is trying to learn, like make in the end making it much more interpretable? Because I think interpretability is a much more of a concern when you're dealing, because RL itself has a lot of usage with end users, like it deals with users' actions, and it's not just one end, like it's continuous, like you are interacting with the agent or multiple agents. Do you see that as a problem in these architectures? And if so, are there any efforts by researchers to solve this bottleneck? I don't know if it's a bottleneck also.
That is a great question. So I don't work on interpretability, so I'm sort of going to be speaking out of my behind here, so forgive me.
Yeah.
I think it's an important problem though. So like for the climate example I mentioned about the operating the grid, there's an issue with that, which is like current human grid operators want to make better decisions, but don't even necessarily understand like uncertainty bounds, which are actually like important to this problem. So like there is like how do we make these systems interpretable is a key bottleneck to having them deployed. I mean, we've seen this in medicine, right? Like making the predictions of cancer detecting models interpretable to doctors is important for adoption. So like it is an important problem. Totally agree. Is RL more interpretable than anything else? Here I'm really just speculating. I guess the thing I could say is like if you're learning a value estimate, so one of the key quantities in RL is like what is the total expected future reward I can expect to get starting in this state and following my policy thereafter. So you can say often you can like plot what the model thinks are like the most valuable states to be in. If you let's say I have a two-dimensional world, I could just highlight the value of each state on top of the states. So in that sense, like there are ways to look into it. You can also look at that quantity for like, given the state, I think taking this action will be the most valuable and something like that. So there may be additional ways to get at interpretability in RL. But like I said, it's not something I'm actively working on. So
Yeah,
I don't want to say too much. Yeah.
Yeah, definitely. Well, what I think is, and definitely it's definitely a discussion. Definitely, I won't pick you if you wouldn't have the most latest of state of art research on that.
That's
But
right. That's right.
yeah, it definitely makes sense, because if you see in deep learning and computer vision, we have these terms activation maps, which is definitely not a very reliable way of putting it out, how making these models interpretable. But it is like a step 101 to trying to at least make a step towards interpretably. So we have these action map that locate and localize which of these parts of or pixels of the image that the model is looking at. When you pose it a cat, if it's totally looking at a different grass, then it definitely is not learning. So I definitely see, and yeah, like you said, like if it can visualize what are the states it's trying to learn, it would be a good thing. But again, when we are dealing with let's say 100 agents, I like definitely researchers might have to work a way around to, because that won't be interpretable for end users to see uh, what it's trying to learn and coordinate with other agents.
Yeah, that's true. And I guess I should emphasize like a lot of the techniques for interpretability that exist in other areas, like doing like input gradients to see like which input maximally causes this output, are still applicable in DeepRL. So benefit
Yeah.
from that.
All right. So I want to take a step back and maybe try to focus on you as of now, apart from being a research scientist at Google Brain. So I want to focus on Natasha Jaques and trying to learn more about what really intrigued you to pursue a PhD. What was the reason that you thought that, hey, I wanna give up 5 years of my life and put myself into a position where I won't have any other life? Why did you? What really intrigued you for doing a PhD?
I don't think the answer is going to be so great, but I think it was basically like, so I was in undergrad and I didn't really, it's sort of a random walk over opportunities is really what it was. When I was in undergrad, I was really good at school. I liked school. I was always like that annoying, like, I know the answer, like student, right? Um, so doing well in undergrad, I got offered like a research internship. So I just did a research internship. I think in undergrad, my first thing was on evolutionary strategies to solve Pac-Man and like various other like pseudo machine learning, but like old school techniques. And then just did a few more research internships across different areas. I did more like I've done a lot of like uh, digital signal processing, like music stuff, weirdly, which I was not as into. And then eventually end up going to a master's degree because that just seemed like the obvious next step. Went to a PhD from there. That was another obvious next step. And so things evolved. Yep.
Right, right. And how did you decide the thesis of your PhD? Was it something that someone suggested, someone uh, maybe inspired you to do it, or was it something like how did you pick up your topic that hey, this is what I'm really motivated, this is something that I really want to do, and how did you end up deciding? Did you have any unsaid uh, other thesis topics that maybe you and advisor only knew, but you didn't end up publishing those things that hey, this is a scrappy idea?
Yes, we did. So I actually, okay, so I interviewed for my PhD with Roz's group at MIT with the following idea. I wanted to make an autism prosthetic. So I wanted to have Google Glass look at the images of the person you were talking to, detect their facial expression, and display it to you. So it would say, this person seems bored. Maybe you should stop talking right now. Something like this. And I just found this. I thought this was going to be so cool. It was much more of an HCI project. The facial expression recognition was not a key focus of the project. You probably use a pre-existing tool. By the time I joined the lab, that was in March or something. By the time I'd actually joined Roz's lab in September, someone else had done that project. I think he actually started a company out of it. So he was at Stanford. I forget his name. I'm sorry. But so that exists, the autism prosthetic Google Glass thing. Although I guess now that Google Glass doesn't exist anymore, I don't know what happened. But that was the idea. Had to pivot. Took machine learning my first semester, and I think you know what it was. Okay, I was originally doing much more like. Okay, I'll tell you the whole story. I'm getting excited about this now.
Yeah,
so
definitely.
I did an undergrad in both computer science and psychology. And I was pretty, psychology was having sort of a replication crisis where studies weren't replicating. And a lot of what I learned in my undergrad was like stuff Freud said, which is to me like not good science. It's like closer to philosophy. I could argue about this, people will be mad, but it wasn't rigorous, right?
I, yeah, I still want to argue, but yeah, definitely for another podcast. Yeah.
Okay. Yeah, but it's or like okay, we did a lot of like reading Piaget's work, which is actually valid, but it was a lot of studies he conducted on his own 3 kids, right? And so it's just like this is not data driven. Like what is going on here? So I had this dream of like I want to use machine learning to understand like psychological questions. And like use machine learning as the next set of statistical tools. Like psychology already uses a lot of statistics. Can we use machine learning to get better answers? So that's sort of where I started. But what happened is I went to my first NeurIPS in 2015 and I just fell in love with it because I was like, oh my God, we're living in the future. Look at how cool this is. AI is real. This is happening. Like I was so excited. I remember some of the papers I saw. This was NeurIPS like 2015. There was a humanoid robot that had learned to climb up on surfaces by like putting its hand on the surface and pushing itself up and then like putting its leg up and climbing up purely end to end with like no prior. And that was just like the most efficient way to get a human body onto a ledge. And I was like, this is so cool. There was end-to-end memory networks, which were like looked like it was doing like analogies and reasoning, which it isn't, but I was excited. And like just a bunch of results where I'm like, oh my God, like AI is so good. Things are really happening. And then I switched. I really moved away from what my advisor works on during my PhD. So that was somewhat challenging. By the time I was like writing up my thesis, which I think is your question, things had changed significantly. And so I think it was more like trying to show the affective computing flavor in the deep learning and deep reinforcement learning problems I was working on. Yeah.
Hmm. Hmm. Yeah, definitely. I mean, I didn't knew about the glass thing that has been done, but I would definitely love to have those glasses as a podcaster because that would really save me many times. So I didn't knew, but yeah, overall, like, well, because how you said is it's more like you had fun around different exploring different projects, but at the end you did something much more of a serious topic that can really scale and you can use it for much more varied application, I would say. So yeah.
Yeah. And so this comes back to a question of like, what kind of impact do you want to have with your work? Because actually, like my original affective computing work, we did a lot of work on better models to predict happiness and health and stress in people, given their like everyday data from their smartphone or their wrist worn sensor and stuff like that. And there was actually like a startup interested in following up on our work and like deploying it. So in a sense, that's like closer to being deployed and touching a real human. And so I think that, in a sense, is pretty meaningful. Now the stuff I'm doing, it's like little dots running around in a grid world. Like, when is this going to be useful, right? But
Yeah.
maybe there's something about like trying to go upstream. Like if you invent something that a lot of other people end up using in various ways, then maybe that's not that I'm doing that, but that would be
Yeah,
interesting.
yeah, yeah, that is one thing that I really agree to that because few of my friends who are working in the task of NLPs and they are trying to understand how to understand the inference between how we talk, right? Like based on the text, what I'm trying to, what does that actually mean? So like humans say certain words in different contexts, and the task over there, like they are not dealing with any kind of these data are generated by randomly. They are not using maybe the scraped elements from outside, and we talk like they lack this particular thing is like we don't know if our research is having any kind of tangible impact. And when on the other hand, when I'm dealing with these data sets, I'm getting MRI scans from doctors, and when I show them results, I'm actually talking to radiologists and chairs of
Yeah.
Alzheimer's associations. So it really feels when they say that, yeah, this is something that we didn't see before, and it feels good. Even though I'm just a first year PhD student, I don't know how the rest of my 4 years are gonna go, but it definitely feels good at the end of weekend that hey, I at least impressed a doctor who didn't know. Like after out of his 30 years of practice, he saw something that I did in like maybe 3 months. So I don't know if he's being modest or if he's really happy with his results. So yeah, I do agree.
I think that's
And
very meaningful. Like, good for you. And I think that's so cool.
hopefully,
You're actually doing something that could help people in the real world. I mean, that must feel good.
hopefully, let's see if I kill a patient for Alzheimer's or versus I save them. Let's see. So yeah, yeah,
I'm sure
and
you will.
and trying to learn more about that the question that I asked was to understand
Mhm,
how did you derive to your PhD thesis is how do
mhm.
you typically right now after your long term of experience of working at places and right now being a senior researcher, I would say in general, how do you if you can figure out a stencil or a pattern for your research approach, how do you go about seeing a topic from a researcher's lens versus segmenting it into deliverables? For example, uh, of course, there are lots of glamorous topics that people can take up and work on, but definitely not a lot of have applications to going about starting it. So how do you typically see a problem if you have a pattern to that is how do you go about segmenting those topics and mapping it to technical jargons that is achievable?
That's a great question. And I'm not sure my approach is the best way to go about it. And I think there's a number of ways you could criticize it. I think some people see a problem. Like, let's say transformers work great, but they're way too memory intensive. How can we make them more sparse or more efficient? And then they try to develop ideas from there by like working on it. I think the way I like to proceed is like I have an idea. Like it has to be like I have like a little Google Doc of project ideas. Like, what if you tried this objective? What would that do? Or like, here's something cool. How would this work? You know what I mean? Like some new algorithm or new way of computing something. And then I say like, okay, if I want to do this project and then I decide to like execute on this idea, even if it's in a new area, I go in and I like read papers for a few weeks to try and like understand what's been done. what's the space of research, maybe like modify the idea, and then just start like building it, executing, running experiments, and eventually write it up. I don't know if that really answers your question, but
yeah, this really maps to the RL environment. Like you have these topics, you have all these rewards, like trying to understand what each of these rewards mean for you, and you try to explore these environments and work on that. So yeah, that was just a funny anecdote that came into mind when you said those things, like you have a Google Doc of all these research ideas. So it
yeah.
really intrigues the RL expert in you. But yeah, that's really interesting. Yeah, yeah. And just one last question that I typically like to have, and which is much more open-ended, that I ask anyone who I invite, is what are some things that you are currently exploring, even if it's not a part of your current work assignment, or I don't know what it's called in industry, but like your assignment that you're working on as a part of being a research scientist. What is one thing that you are tailing your research to learn more about what people are working, and that really excites you, even though you might not be directly working on? What is one thing that you see that, okay, I want to see how this pans out in the next 6 months?
Yeah. Well, one thing I want to see that pans out in the next 6 years or more is like hierarchical RL. I really think intuitively it makes a lot of sense, and you should have hierarchies. And there's like some evidence that the human brain uses a lot of hierarchies, and it's like a good way to like structure a model. But it doesn't work, and people have been trying to get it working for many years. And I told this to like a very senior RL person, and he was kind of like, "Cool, like I've heard this before." So we'll see if that actually pans out. Something a little closer to home is like language conditioned RL, or integrating language models into RL to get better generalization. So if you can encode a bunch of human knowledge into some interesting model by training on a bunch of text on the internet, how can you use that to improve RL? I also think it's kind of important for like human AI interaction. So, I mean, it's obvious for this web navigation problem we talked about before. Okay, Google, buy me a keyboard. Well, what does that mean? What is buy me a keyboard? How do I actually listen to what the human is saying? Or more interestingly, like if you had like a humanoid, like an autonomous household robot, and it says, go unload the dishwasher. No, the bowls go in the cupboard or something. Like understanding that, I think, is like a really interesting problem. So that's actually something that I'm starting to get into.
Yeah, definitely agree. The NLU part, the natural language understanding, and it seems promising. Applying reinforcement learning to that will be marvelous. So thanks for sharing. But so far for the podcast, these were the questions I had, and definitely I really had fun. Most of the questions that I asked were not a plan of the stencil that I had, so definitely fun talking to some of the in-between thoughts of a researcher and trying to learn more about your journey as a PhD student to senior researcher, I would say, to right now working at Google AI. So it was really fun, and thanks for sharing all these insights and your current works. It was really fun talking to you.
Well, it was really fun talking to you too. Thanks so much.